Hey, good morning. We are still looking at analytical applications of the derivative. We're technically in Unit 5, not Unit 4 at the top there. But today we are graph sketching and looking at asymptotes. So we will use derivatives to determine the parts of the graph and actually sketch the graph. And this should say without a calculator. You're going to do this by hand. There are actually only 4 curves that make up any graph that you see. There is increasing concave up, decreasing concave up, increasing concave down, and decreasing concave down. Those are the 4 pictures, the 4 curves that we use to make any graph. If we were in my classroom, I'd have them on a big poster in the front of the room and we would point to them. But we are going to use everything with the first and second derivative. We're going to fill out this table and we're going to attempt to graph this. So I have a quick pause here and then I'll be right back. All right, so example 1, sketch 1/3 x cubed minus 1/2 x squared minus 2x plus 3. The first thing we need to do is look at critical points. Where do critical points come from? The first derivative. So f prime of x is going to be x squared, because 3 times 1/3 cancels out, minus x, 1/2 times 2 cancels out, minus 2. We're going to set this equal to 0, and this factors. X is equal to 2 and x is equal to -1. These are the critical points. And then we put those on a number line, if you recall. There's my -1 and my 2. And we want to try in between values into the first derivative to look for increasing and decreasing. So less than -1 is a -2. If I put it in for here, I have a negative. This is a negative, and negative times a negative is a positive. Between -1 and 2 is 0. I'm going to actually put it in up here for both of these. 0 minus 2 gives me a negative, and larger than 2 is a 3. If I put it in for x and x, this is a positive times a positive, which is a positive. So x equals -1. If I switch from increasing to decreasing is a max, a local max. And x equals 2. If I switch from decreasing to increasing is a local min. Everything you need with that first derivative. Oh my goodness, can't erase just one thing at a time here. And critical. Okay, so over here on this table, we're actually going to put in some points. I don't think our table is quite big enough. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. I'm going to put one more row out here, one more column. So on our table, we have a -1. I'm going to come back to the table. Hold on. I'm going to come back to the table. I'm not exactly sure how that's going to work out yet. All right, so we have everything with the first derivative. Actually, we can talk about increasing and decreasing. We're increasing from -1, negative infinity to -1, and from 2 to infinity. We are decreasing between -1 and 2. All right. That's everything with the first derivative. Now we have to do everything with the second derivative to talk about concavity. So we'll do it all again. The second derivative is 2x minus 1. When we set it equal to 0, we get x is equal to 1/2. This is not a critical point. This one is your inflection point. Let's do the number line again. Second derivative. Here's my 1/2. A number less than 1/2 is 0. If I put 0 into the second derivative, I get a negative. If I put a number larger than 1/2, say 1, into the second derivative, I get a positive. So we are concave up from 1/2 to infinity and concave down from negative infinity to 1/2. Now we want to take, whoops, sorry about that. We want to take all this information and organize it on the table that we have up above. I'm going to show you what that looks like in just a moment. Okay, so on the table, what I have put is I've put my inflection point right here, and I've also placed my critical points right here and right here. And then just as a reminder, I've got negative infinity and positive infinity. They're not really part of the table, but just what's to the left of -1 and what's to the right of 2. We are going to transfer the information from the table, from the number line that we did.
We are done with that.
Sorry for interruptions today. All right, trying to get things situated in my house. All right, so the number line goes into the table. So we're positive to the left of -1. We're negative between -1 and 2. And we're positive between 2 and infinity. So it looks like this. Now, the other thing I'm going to add is we have a 0 at -1. That's where we had a critical point. And we had a 0 at 2. That's also where we had a critical point. So my table's a little bit messy. Now, the information for the second derivative. On the number line, to the left of 1/2, it was all negative, concave down. To the right, they were positive. And at 1/2, it was 0. This is my inflection point. So this is a reminder, here's my inflection point. This is a critical point. And this is a critical point. Now, I'm going to shrink out here a little bit. This chart on the top, if you can print that out, if you can duplicate it on a Post-it note, put it somewhere with your golden ticket, it will help tremendously with these problems. It will help a whole lot. And in fact, if this were in my classroom, I would call this one curve A, curve B, curve C, and curve D. And we talk about them together. For this first section, I'm increasing concave down. First derivative is positive, second derivative is negative. So increasing concave down. So you want to ask yourself, which of those curves is increasing concave down? Well, it's curve C. So I'm going to use this box and just write in a curve C. In that second region, I'm decreasing concave down. So which one of those curves is decreasing concave down? It's curve D. And then I'm decreasing concave up. That's this region. Decreasing concave up. So which one's decreasing concave up? Is B. And then I'm increasing concave up. And that's the last section. That is curve A. All right, so we have the 4 curves that make up our graph. I'm going to zoom out a little bit more. Now, I have the basic shape, and I know that we have a critical point at -1. I have a critical point at 2, and I have an inflection point at 1/2. But I need to know how high or how low these go. So what I'm actually going to do is find f of -1. I'm going to find f of 1/2 and f of 2. That will give me 3 places on the graph where I can anchor this whole thing. So I'm actually going to pause the video while I do that. Okay, so I have found f of -1, f of 1/2, and f of 2. Now these don't wind up to be nice, neat integers, but that's okay. I'm just looking for estimates. And truthfully, I'm not so concerned about the y values at this point. I'm much more interested in the curves. So -1, 4 is -1, 1, 2, 3, 4, up a little bit. 1/2, 9, 1.9 is like right here. And 2, -0.3, I know that's really messy. 2, -0.3 is kind of like right here. So if I take those curves that were in the table up above, this is increasing concave down. Then I hit that max. Then decreasing concave down. Then I hit the inflection point. Then decreasing concave up until I hit the minimum. And then increasing concave up until I go to infinity. So there's the graph. And this is a nice, neat polynomial. It's a cubic function, which makes sense, right? Because this is x cubed. And you can check your work in the calculator. Now, being as we're working at home, I know you have access to your calculator for all these problems. But when you go to take the AP exam, you will not for some of them. Are they going to ask you to go through and sketch things like this? No, but there will be a lot of curve analysis. Tell me about increasing, decreasing, concave up, concave down. So it's important that you know all the steps all the way through. Let's look at another example. Trig functions. Sketch f of x equals cosine x plus 1/2 x between 0 and pi. So we want to do all those steps with that first derivative. The derivative of cosine is negative sine of x. The derivative of 1/2 x is 1/2. You're going to set this equal to 0. And to solve this, I'm going to move the sine of x to the left. So sine of x is equal to 1/2. So this is where you have to ask yourself, where does sine equal 1/2 on the unit circle? Sine is the y coordinate. I have to think about this one. This is root 3 over 2, 1/2. And we're only between 0 and pi, so we're just on the upper piece of the unit circle. And then over here, I've got a negative root 3 over 2 and a 1/2. So you have to ask yourself, what are those angle measurements? I know it's not the pi over 4, it's not the 45 degrees. So is it the 30 degrees or is it the 60 degrees? It's the smaller one. This is the 30 degrees, which is pi over 6. And then all the way over here to 5 pi over 6. Yes, the unit circle is something you should definitely have memorized. So x equals pi over 6, x equals 5 pi over 6. These are your critical points. Okay. Ooh, what else? We have to figure out if those are maximums or minimums, right? So I almost forgot the number line. Now, these don't go to positive and negative infinity. Keep in mind, we're only dealing with 0 to pi. 0 to pi. So if I choose a number that's less than pi over 6, it doesn't have to be greater than 0. You can actually include 0. Those brackets mean 0 is included. So if I put 0 into my first derivative, sine of 0 is 0. 0 plus 1/2 is a positive. Between pi over 6 and 5 pi over 6 is pi over 2. So sine of pi over 2 is 1, but a negative 1 plus 1/2 makes this a negative. And greater than 5 pi over 6, I'm going to use that pi value. Negative sine of pi is 0. 0 plus 1/2 is a positive. So x equals pi over 6. If I go from increasing to decreasing is a maximum. X equals 5 pi over 6. If I go from decreasing to increasing is a minimum. And I'd also list I'm increasing between 0 and pi over 6, and also between 5 pi over 6 and pi. I'm using brackets on the 0 and the pi and parentheses on the other values. I am decreasing between pi over 6 and 5 pi over 6. Okay, that's everything with the first derivative, and I didn't leave myself enough space. So I'm going to take all of this and shrink it. Okay. Maybe I can shrink it. All right, we got the first derivative information tucked up there. We know where the max is, the min is, increasing and decreasing. So let's do this again with the second derivative. So my second derivative, the derivative of negative sine is going to be negative cosine of x. The derivative of 1/2 is 0. So we set this equal to 0. So cosine of x is equal to 0. So you have to ask yourself, where does the cosine of x equal 0? Well, cosine is the x coordinate on the unit circle. The x coordinate equals 0. All right, so we found the inflection point is x over 2 for cosine of x. Now, our next step is to create the number line. So here's our number line. Here's, I said x over 2, pi over 2. We're going between 0 and pi. Now, for this step, to find concave up and concave down, we have to use the second derivative. So less than pi over 2, I can use 0. I can use pi over 4. Pi over 4 might be a good idea. So negative cosine of pi over 4, put it in here into the second derivative. So cosine of pi over 4 is root 2 over 2, but I have to make that negative. So I have a negative. And then over here on the right-hand side, I've got 3 pi over 4. Cosine of 3 pi over 4 would be negative, but the negative in the front makes this whole thing positive. Now, I had moved ahead and made a bit of an error. We're going to get rid of all that. So we are negative, negative, 0 for my inflection point, positive, positive. Now we want to fill in those curves like we had up here at the beginning. But unfortunately, I can't show them both at the same time. So if we put the curves in, increasing concave down looks like this, decreasing concave down, decreasing concave up, and increasing concave up. So those are the 4 curves in the order that we have them. Now, if I mark out the critical points, it happens at pi over 6 and at 5 pi over 6. And we're looking at an inflection point at pi over 2. We're only graphing between 0 and pi. We're only graphing between 0 and pi. Now, I'm not going to take the time this time through. I guess I could. If I put 0 into the original function, if I find f of 0, cosine of 0 is 1, plus 1/2 times 0 is 0, so cosine of 0 is 1, so f of 0 is 1. This passes through, I'm going to call this point 1, and this is -1. So I pass through 0, 1. This is the starting point for my graph. That might be helpful. So between the starting point and that pink line, I'm increasing concave down. Then we're decreasing concave down. Then we're increasing concave up and increasing concave up. Now, I didn't go through to find the other values at, say, pi over 6, 5 pi over 6, and pi over 2 to really anchor this graph to figure out how high or how low it should be. Pi over 2 might be helpful. Cosine of pi over 2 is 0. That's handy. And then 1/2 times pi over 2, that would just be pi over 4. That's about 0.75. So my graph probably goes a little low. It should probably be 0.75 would be up here on my graph. So this might look a little better. But if you wanted it to be very accurate, you would go through and find your y values. Now, just get rid of this and this. Be kind to yourself. Remember, it's a sketch. Draw a little loosey-goosey the first time, and you might have to go over it again. You might have to adjust it, use the eraser on your pencil. It's not going to be perfect the first time. All right, trig functions, that was fun. And rational functions, also a good time. I think this is the last one I have. Yes, it is. So we want to do everything with the first derivative to find critical points, increasing, decreasing. So let's say that f prime of x, I'm going to use a quotient rule, the bottom, derivative of the top minus the top times the derivative of the bottom over the bottom squared becomes -2x over x squared minus 1 squared. I'm going to set this equal to 0 and solve for x. Now, sometimes I get to this point and ask students, what do we do next? And they get a little stuck. But if I put 0 over 1, they tell me cross multiply, no problem. 0 equals -2x. So 0 is equal to x. This is a critical point. But we also have to check for other critical values. We have to check the denominator. So I'm going to say 0 is equal to x squared minus 1 squared. We have to know, well, where is that first derivative undefined? You might have a vertical asymptote, or you might have a cusp. You don't know at this point. You can figure it out. But we're going to take the square root of both sides. We're going to add 1 to both sides, and x is equal to plus or minus 1. Now, if I come up here back to the original, let me use a different color. 0 equals x squared minus 1, x equals plus or minus 1. I can't divide by 0. It's not in the domain. Those are vertical asymptotes. But if they're vertical asymptotes, they're not technically points on the graph, but they are locations where that increasing, decreasing can change. So we still need to include them on our number line. So we are going to look at 0. I'm going to make my vertical asymptotes orange here, -1 and 1. And we're going to substitute into the first derivative. So you can use this version up here. That's pretty good. If I choose a -2, the numerator would be positive. Here's the cool thing about the denominator. It's squared, so it's always positive. So this works out to be positive. If I chose a -1/2, -2 times -1/2, that would be positive. If I chose a positive 1/2, that would be a negative. And if I chose a positive 2, that would be a negative. So we are increasing from -infinity, include the stop at 1. There's a -1, there's a vertical asymptote there. And -1 to 0, we are decreasing from 0 to 1 and 1 to infinity. X equals 0. I go from increasing to decreasing is the local max. And x equals -1 and 1. Those are vertical asymptotes. There's no switch there. All right, that's everything for the first derivative. For the second derivative, we have a quotient rule and a chain rule. So I've got x squared minus 1 squared at the bottom times the derivative of the top minus the top times the derivative of the bottom. There's my chain rule all over the bottom squared. So it's x minus 1 squared squared, which is to the 4th. Don't cancel anything out here. I know it's tempting. I know you want to. You can factor to simplify. I'm going to factor out an x squared minus 1. So I've got x squared minus 1 to the first times a -2 and -2x. The 2, the x squared minus 1 got pulled to the front. There's another 2x. All over x squared minus 1 to the 4th. Now I can cancel. Now it's safe. This cancels with one of these. So I've got -2x squared plus 2. And then this is plus 8x squared all over x squared minus 1 cubed. And this is 6x squared plus 2 over x squared minus 1 cubed. That's a whole lot for the second derivative. In order to find those inflection points, we have to set this equal to 0. So just like with the first derivative, multiply the bottom by the denominator. And I've got -2 is equal to 6x squared. X squared is equal to a -1/3. X is the square root of -1/3. Well, what does that take you back to in Algebra 2? That's an imaginary number. Here's the good news. We don't care about imaginary numbers in calculus. For us, that means no solution. So I know all that work and you came up with no solution. But you actually still want to check the denominator again. You have to see where that second derivative is undefined. So I'm going to take the cube root of both sides. We got x squared minus 1. 1 is equal to x squared. X is equal to plus and minus 1. Where did we see that before? Oh yeah, those are the vertical asymptotes. But they are places where your concavity can change. So let's do the number line. -1 to 1. We're dealing with the second derivative. If I choose a -2, excuse me, for the second derivative, the numerator is positive. The denominator is also positive, so positive over positive. If I choose a 0 for the second derivative, I get a negative. If I choose a +2, I get a positive again. So we're concave up between -infinity and -1, 1 to infinity, or concave down from -1 to 1. Awesome. In inflection points, it depends on the text that you read. Are there inflection points, yes or no? The argument for no is there's no point on the graph where concavity changes because it doesn't exist. -1 and -1. -1 and +1 are not in the domain, but there are inflection values where the concavity changes. So it depends on which textbook or which resource you're using to look that up. I've seen it defined both ways. So inflection point, technically not an inflection point, I would say, because it's not in the domain, but there is a value where that concavity can change. Now, we have to put all of this on the table, so I'm going to have to zoom out here a little bit. We've got -1 and 1. -1 and 1. Those were those vertical asymptotes that we talked about and kept showing up. And then we had a critical point at 0. So this time on my table, because these are vertical asymptotes, I would say does not exist. Does not exist. Does not exist. It's where we were trying to divide by 0. For that first derivative, let's make this a little bit more readable. Sorry, guys. It was positive, positive, negative, negative. And then the second derivative was positive, negative, negative, positive. Okay. Remember those curves on that first page? Increasing concave down. Let's do all of those. Let's use brighter color. Increasing concave up would look like this. Increasing concave down looks like this. Decreasing concave down looks like this. Decreasing concave up looks like this. We had vertical asymptotes at negative and positive 1. Actually, let's make those orange. Okay. Vertical asymptotes at positive and negative 1. Now, the easiest one to probably do is between negative 1 and 1. We didn't talk about horizontal asymptotes, though. That's actually very helpful here, and we haven't really chatted about those since limits. So let's back up and talk about horizontal asymptote. As a reminder, it's the limit as x approaches infinity. So if I put infinity in place of the x, I've got 1 over infinity squared minus 1, which is 1 over infinity. And what do we say a number over infinity is? 0. So y equals 0 is a horizontal asymptote. I like him, buddy. No, that's perfect. Good job. Go listen to your arrays. Sorry, a little interruption there. If I put 0 into the original function, if I find f of 0, I get a negative 1. That's a place to anchor this graph. So the curve to the left would look like this. The curve to the right looks like this. And then the question is, this increasing concave up, does it look better here? Or, oops, don't do that. I actually want it to be curved, friend. Or does it look better? All right, hold please. Let's try again. Or does it look better down here in quadrant 3? Quadrant 2 or quadrant 3, based on those asymptotes that we have. On the horizontal asymptote, I actually think it's best here. So we have that last region to the right of 1. Again, you want to ask yourself, does it look better down here in quadrant 4? Or does it look better up in quadrant 1? So there it is in quadrant 4. Here it is in quadrant 1. I know this is not very mathy, but I'm going to say it looks better up here in quadrant 1. You could technically pick a value, say 2. Put 2 into the original function. 2 squared is 4 minus 1. This is 1/3. So you had the point 2 1/3, which is above the x-axis. So you know it has to be up in quadrant 1. So there you go, curve sketching. Are you going to have to sketch a curve on the AP exam? No, but we know the College Board is going to have a very crazy way to make sure that you know what's going on. They're going to ask all kinds of questions about the first and second derivatives. These are long problems. They're complicated. Be patient. And if you get stuck, reach out with questions.